Hello, everyone. I'm John Langford. I'm joined by Katja Hofmann, Hoifung Poon, and Jianwei, each of whom is working on multimodal models of actually quite different varieties. So the topic that we're going to be thinking about is multimodal models and where the future is. I guess I'd like to start with what do you see as kind of the key benefits and uses of a multimodal model? Maybe we'll start with Hoifung. Can you tell us give us the background of where you were at with multimodal models, what you're working with them on, and where you see them really shining?
Yeah, thanks, John. Very excited to be here. As John, you mentioned, one of the really sort of like really exciting frontier is to advancing kind of multimodal generative AI. And for us, a particular exciting area is to apply this into precision health. And cancer is really sort of the poster child for precision health, right? So for example, one of the really cutting edge treatment for cancer these days is immunotherapy that works by mobilizing the immune system to fight the cancer. And then one of the blockbuster drug is Keytruda that really can work miracle for some of the late stage cancer. And the annual revenue is actually above $20 billion. Unfortunately, only 20 to 30% of the patient actually respond, right? So that's really sort of like kind of like a marquee example of what are the growth opportunity in precision health. One of the really exciting, if we look back the past couple of decades, one of the really exciting thing happening in biomedicine is that the rapid digitization of patient data that go from medical imaging to genomics to medical records, clinical notes, and so forth. So every day, if you look around, there are literally billions and billions of data points collected in sort of like clinical care, right? Routine clinical care that documenting this very high dimension patient journey from diagnosis to treatment to outcome. And for example, a cancer patient may have hundreds of notes, but also crucially, it would have information from like radiology imaging, like from CT to MRIs and so forth. And by the time when the cancer patient get biopsies or recession, then you will also get digital pathology, you will get genomics and so forth, right? So one of the really exciting opportunity is that all this kind of modality are trying to tell you something about the patient, right? But each of them are very limited in its own right. So I like to liken it to sort of like blind folks touching the elephant, right? So each modality give you one piece of the elephant, and only by sort of kind of like combining all those modality, and we can recapitulate sort of like the holistic representation of the patient. So that's sort of like what we see the most exciting opportunity is to can we learn from real world data at the population scale to be able to train very powerful sort of like frontier biomedical model that can create this kind of multimodal patient embedding that synthesize a multimodal longitudinal journey of a patient to essentially can serve then as a digital twin. Then you can start to reason about it to find patient like me, right, and at population scale to figure out what works, what doesn't work, and so forth. So we start to actually see some of the promising kind of proof point by working with like large health systems and pharmaceutical company, clinical researchers, and so forth.
So fusing different modalities to get a holistic picture of the patient in order to analyze what kind of treatments may work and so forth.
Precisely,
Yeah.
like the very minimal is that you can start to leveraging that very high fidelity patient embedding to like for example today for cancer patient people would like, oh, let's go find a second opinion, right? With this at the population scale you can get 5 million second opinion, right, to find all the patient like this person, and now you can interrogate what are the treatment that people have tried, right? And what actually work, what doesn't work. Now you can start to make this better decision making, so that's the immediate benefit. But more importantly is that you can start to also, like for example in the Keytruda case, you can start to interrogate who are the exceptional responder versus those 70%, 80% are non-responder. How are they differ, right? And And that would give you a lot of clue about sort of like why the existing drug and target doesn't work, and that could potentially drastically accelerate kind of discovery.
All right, thank you, Hoifung. Katja, do you want to tell us a little bit about your multimodal models?
Sure. Interestingly, the kinds of applications in the space we've looked at in my team is very, very different from those applications in precision health that Hoifung just mentioned. We have looked at one of these fundamentally human activities of creative ideation. And we've been exploring the potential of generative models for this in the context of game creation. So crafting, coming up with new ideas for video games is something that, of course, people are doing on a very regular basis. There are 3 billion players on the planet that rely on getting very diverse, engaging content in order to create these really immersive or connecting experiences. And what we've seen looking at generative models for this is that, one, there is a huge potential for that, but at the same time, we still need to push on capabilities of these generative models. For example, in order to support divergent thinking or to allow people to iterate and really control the kinds of things that these models are able to produce. In my team, we have focused on initial models that are multimodal in the sense of modeling both the visuals of what a player might see on the screen, as well as the control actions that a player might issue in response to what's on the screen. So those are the two modalities that we have so far. And with the models that we have trained in this space, we see that they have this amazing capability of picking up for example, an understanding of the underlying game mechanics, how different characters interact with each other, and they also provide some amount of ability to be modified by their users. So, for example, creatives could inject new characters or new components and then just work with this material to envision how different gameplay situations might work out. So I see a lot of potential for models like this to support creative ideation in many different application domains. And over time, we will understand how we can add additional modalities to this kind of material for creators. And I think we're only at the beginning of exploring what's possible and what new kinds of things people will come up when they have this new material at their disposal.
So just relating to Hoifung's, it seems like Hoifung probably deals with a lot more data access and incomplete data type of issues than you may be dealing with. But then there's also kind of a creative dimension of things never tried before, which you would like to address that maybe is not so important in Hoifung's case.
That's a really good reflection. I think this already points to some of the key both challenges and opportunities in this space. One opportunity is just the fact that Hoifung and my work is in many ways so similar. Is really quite striking. We've seen a kind of confluence of models in the sense of we have a really, really good understanding of some of the things that work really well, especially when we have the right data and when we know how to scale them up. But there are also some fundamental questions on how do we deal with partial and complete data? How do we curate and create data sets? How do we understand the impact of the variety, quality, and scale of data that we have at our disposal on the ultimate quality of the models that we can create? In our case, like you say, we build on kind of the rich data that we can obtain from game environments. And that also means that we can inform some of those research. We can build insights on how to best use this kind of data that might actually benefit Hoifung and his team in building better models ultimately for precision medicine, which I find incredibly exciting. And then there are dimensions where we really look for very different things. Precision, of course, accurate results is very, very important for any application in the health space. Whereas in our case, for example, capturing the full diversity of what might be possible in a given game situation, or pushing on boundaries, creatively recombining elements is something that we might be looking for that may be much less desirable in other applications.
All right, thank you. Jianwei, can you tell us about your multimodal models?
Yeah. So hi everyone. Yeah, I'm very glad to be here to discuss about the multimodal model. So my background is more from computer vision. So I started my computer vision journey roughly maybe 10 years ago, and now actually we are mainly talking about the multimodal model. So typically actually the multimodal model actually are mainly covering about, for example, the vision and the language and how we can combine them together. And in my opinion, I think at a high level, this kind of multimodal model actually can really help in a lot of kind of applications or a lot of kind of scenarios in that it can really help to capture the world surround us. So it have the visual input and it can capture what kind of object in it and what kind of relationship and what kind of action in the image or videos, etc. And on the other hand, actually this kind of multimodal model, by connecting this vision and the language, can really help the model have the communication capability with human, so that kind of human can really have a conversation and can chat with the model and then prompt the model to really finish some task that the human or the user is requiring it to. So overall, I feel there are a bunch of applications for in this kind of multimodal scenarios. So from my point of view, so at a high level, it can be applied to not only the digital world, as Hoifung and Katja just mentioned, his and the gaming scenario, but also it can be applied to the physical world, right? So if we really have a multimodal system or AI agent that can really understand the whole environment, the physical world, and then have a very good communication capability, actually it can be deployed to, for example, autonomous driving system or even a real robot, right? So that we can really have a very good kind of co-pilot or something like that, so to help us to do a lot of daily tasks. So this is quite exciting domain, but also actually we are still just at the beginning of this journey. Yeah.
So, relative to what Katja and Hoifung talked about, are you thinking about more general purpose multimodal models, or are you thinking about individual special case ones for each of these individual applications?
Yeah, I think that's a very good question. So I think all of these application scenarios actually share some kind of basic rules. So in terms of the model building, actually, we really need to care about the data, care about the modeling. So I will roughly talk about the modeling part. So to really, have a capable multimodal model, we need to encode different information from different modality, for example, from vision, from language, from even audio, speech, etc. So we need to develop a very capable encoder for each of these domain, and then how to tokenize each of these raw data, right? So the pixel is raw data, the speech is raw data, and then we need to develop some good model to tokenize each of the modality so that we can project all of this modality into the same space and model the interaction across different modality data, so that it can be really used to accomplish some complicated task for each of the domain. So in my opinion, I think we have shared a lot of kind of common interest across different applications. For example, in our team, actually, we have been doing a lot of researches towards the general purpose multimodal system, and in the meanwhile, actually, we have a great collaboration with Hofmann's team to deliver some kind of domain-specific model, like LavaMed, like Biomedical Journey, etc., for the conversational medical AI system, and also for the medical image generation and editing or prediction. So all of these kind of are sharing some kind of basic component in terms of modeling. Yeah.
All right, thank you. Maybe a question to kind of sharpen the discussion here is, what is sort of the top one multimodal challenge that you guys are running into? And Hoifung, maybe you can start.
Sure, happy to. And first, I want to echo Katja and Jianwei So I think one of the really exciting thing I think is that sort of like a lot of the commonality, right? And in a lot of this work, and I think that also speak to sort of like a more kind of general trend in AI that people kind of call it at some time like great consolidation in AI, right? So for example, like I come from NLP background, Jianwei come from computer vision background, right? We could be friends in the past, but we probably rarely share a lot of the actual kind of modeling technique in the past. But these days, like a lot of the underpinning across this different modality, right, are actually quite common. For example, powered by transformer, at least as one of the prominent paradigm, right? So that really opened up a lot of the kind of like, cross pollination, as Jianwei and Katja alluded to, right? And because you can use transformer to model imaging, you can model video, model text, model protein sequences, and so all that. So so that's a super exciting thing, and that's what you see across the board is like you see some breakthrough in one of the modality, and often very quickly some of that can translate to some other, right? Now back to your earlier question, I think, and one thing as you alluded to earlier, right, John, is that in biomedicine, I think there are some specific challenges. Number one is actually sort of like a lot of this, like obviously are very high stake. So we have to take utmost kind of care about sort of like privacy compliance, right? So for example, all of our collaboration, the data and all the compute actually happen in our partner. Like for example, health system is strictly within their tenant. And we work within their tenant to collaborate with them. So make sure that all this, are super buttoned up. And then so there are some kind of like immediate sort of like pragmatic challenges, and then also if you look at the sort of the kind of like across the board, there is some infrastructure challenges, right? Like for example, before the day when a lot of those data are actually on the cloud, it's very difficult, right, to do a lot of the on-prem computing. But nowadays, that because a lot of those data start to get into the cloud, that make a lot of this kind of AI progress a lot easier to apply. And then from a specific kind of like modeling challenges, we benefit a ton from the sort of like general domain progress, right? First and foremost, right? So a lot of our kind of basic modeling actually, like that's why we build on a lot from Jianwei and his team's great work, right? However, also when you look at the biomedicine, and there are also very specific challenges. Like I would start from a individual modality, right? So for example, if you look at like the current frontier model, let's say, GPT-4s and so forth, they are actually really good at reasoning and understanding biomedical text, right? But once you go beyond sort of like go to the non-text modality, once you look at CT, MRI, digital pathology, omics, and so forth, then those frontier models is exposed their competency gap. And the challenge is that biomedical text, actually, there is a ton on the public web, right, that GPT-4 was able to consume. Like PubMed alone, right, have 32 million biomedical papers, right? But when you think about like multimodal longitudinal patient data, those are not really, exist a ton in the public web. So that creates sort of like lots of kind of competency gap. And so and there are lots of unique challenges. For example, take digital pathology as an example, right? A pathology whose slide images could contain billions and billions of pixels, right? And it could be hundreds and thousands of times larger than a typical web images. And that means like standard way to use transformer completely blow up, right? Because you probably need, quadratic, which means like billions of time of compute for a single image, right? So and CT and MRI are not 2D images, and they are also very different from 3D video. Normally you will find in the general domain. So all those are kind of like present very exciting challenges for individual modality. But then so that create a lot of exciting research opportunity by saying, hey, what are some of the modality specific inductive biases, right? And that we can harness to do modality-specific self-supervision, pre-trainings, and so forth, right? And so we can do effectively, dimension reduction in individual modality. But once we do that, there are still a big challenge, as Jianwei alluded to earlier, which is that, for example, think about it, right? Like a tumor lesion, right, in the CT images may be mapped to a very kind of different space in the embedding space compared to the tumor lesion in digital pathology, because they are kind of like independently self-supervised pre-training. So then come up actually another, and I would say even much bigger challenge is like, how do we handle this kind of multimodal complexity, right? So how can we ensure, sort of as Jianwei alluded to, how can we ensure that those tokenization for individual modality, they are actually aligned, and actually, so now you can actually put them together to start doing effective multimodal reasoning, right? So like from an NLP background, you can think about this as a little bit like in translation, right? So the world has hundreds, if not thousands, of languages, and one of the key challenges is how can we enable sort of like communication across those languages. And one of the very effective approach, right, that machine translation community have come up with is this idea of introducing a resource-rich language as an interlingual, right? So, for example, if I have a language from Africa versus a sub-language in India, then maybe it's pretty much like zero pairwise data between them, right? So I don't know how to translate between them. But if I can actually learn to translate that African language into English, and then translate from English to that sub-language in India, then we would be able to successfully bridging the two languages. And in multimodal, there is actually, we see an emerging opportunity to do the same thing. And we basically are using the text modality, right, as the interlingual. And the reason is that for any modality under the sun, the study of that modality typically involves a natural language. So when you get an image, like radiology image, you often have accompanying radiology report. When you have a digital pathology slide, you usually have a pathology report, right? So then you can using that language as a sort of a natural language supervision to grounding the embedding, to nudging the embedding space on the individual modality to the kind of like sort of the common semantic space represented by the text modality. And also in this way, we can also capitalize on the dramatic investment in the frontier model that are very, very good on the text modality, right? So then if we can really align, make sure that all the modality roughly align their common concept into the text semantic space, then that can make the reasoning much more kind of like easy. And a lot of this actually, like for example, Jianwei mentioned about the LAWA network, right? That really sort of inspired by the general domain LAWA work in vision language modeling. But then we can actually generalize that into biomedicine to start using that modality text pair to ground the individual modality.
Yeah. So a couple comments. One of them is what you described at the beginning. I've heard described as the Great Convergence. So it used to be that there were vision conferences and NLP conferences and machine learning conferences, and there still are. But at the same time, suddenly what's going on in these other conferences are very relevant to everybody. And so it's interesting. It's suddenly lots more things are relevant than they were previously. And then amongst the different challenges you mentioned, I'm going to pick, I think, on the competency gap, because it seems like it's an interesting one that kind of applies potentially across many different folks. I think that the high stakes nature of medical situations is also a very important one, but specific to the medical domain. So the competency gap I've seen described elsewhere, and there's been a number of studies and papers. It's an interesting challenge, definitely. Katja?
Can you remind me what you mean by competency gap? I missed that.
The competency of these models in the vision modality is not as good as they are typically in a text modality. In a text modality, they're pretty good in a lot of situations. But in the vision modality, there are simple things like, what's the relationship between this object and that object in the picture, where these models can just not really succeed.
Yeah, so specifically, Katja, right? Like for example, and first, as John alluded to, right? So for things that beyond text, let's say image and speech, right? So and even in the general domain, there may be sort of like already some challenges that could actually certainly have growth space. But once you go to a vertical space like biomedicine, then those competency gap are actually much more pronounced, right? So if you ask some of the state-of-the-art image generator to say, "Hey, draw me a lung CT scan," they will actually draw you a glowing lung, right? It has no idea what is a CT scan, right? So and across the board, you can see this like there may be some particular classification task or something where some of those data are actually in public, right? So there may be some academic data sets and so forth. So in this case, the frontier model may have seen them and been exposed to them, so they may have been able to internalize some of that, right? So if you ask some of the really top frontier model, they at least have some idea like, oh, this should be X-ray, this should be a CT scan, this should be, right? And sometimes maybe even some detailed information, maybe it also have some idea. But once you go really deep into those, like, hey, what is tumor lymphocyte infiltration, right? They have no idea, right? Because and you can argue also like it's very difficult to wait for the frontier model to, let's say, wait for it to actually parse all the quality token in the public web, because a lot of those kind of multimodal patient data are simply not existent, right, in the public web for a good reason, right? So that basically put a very kind of important responsibility for us to figure out what could be a scalable AI methodology for us to quickly, efficiently to bridge those competency gap for individual modality and also for enabling combination, synthesizing all of them, as Jianwei alluded to earlier.
So Katja, what's your top one challenge?
There are many challenges. I found myself agreeing with Hoifung on many of them. And I was going through a couple of reactions. So let me start with thoughts on the competency gap and also that interlingual, whether natural language is going to be I don't know, shared modality connecting across all of them. I was just, as you were speaking, thinking through that it's weird in the sense that some of our key insights in this space come from large language models. So really a model that is started because that data was most readily available, maybe we have a lot of our insights from specifically language, which of course in our own human experience doesn't come first. We experience the world through vision, touch, and all our other senses before we start to make sense of any of the language that is spoken around us. So it's really interesting to think through the implications of that. And potentially, as we start to understand more about the different modalities that we can model and the different ways in which we combine them, some of those initial insights may no longer hold. In our examples of gameplay data, we start from visuals and controllers, and we get this really highly consistent model that is able to generate 3D space, how characters interact with the space, how game mechanics work, causal effect, and things like that, which is something that is quite different from what has been observed in many other models. So I think there is quite a lot of hope to kind of that we will be able to arrive at models that have a much more holistic understanding of how the world works once they no longer rely on language as their primary sense, for example. And because of that, I'm also not sure whether indeed natural language will be that shared underlying thing that unites modalities. There might be other better choices for that because language it is abstract. It can capture so many things, but it might not be the most efficient way of communicating a lot of the things that we can grasp in other modalities. So I'm really curious where that is heading. But coming back to your question, John, on what I see as the biggest challenge, it feels like we're at such an early stage in this field. I could map out tens, hundreds of questions that are really, really interesting, starting from representations and data to model architectures, to the way in which different model components might be trained separately and might interact in kind of societies of models or agents, if you will. But what I like to bring this back to is that for me personally, the way we ultimately use those models, the way we understand how they can fit within our kind of human practices, to really make sure that when we build these models and they have the potential to change the way we do our work or play games or interact with each other, that we should be focusing on making sure that they are as useful, as empowering to their users as possible. And so I think we could do a lot more in understanding not just purely what we can build, but also what is the need? What are the kinds of capabilities we need to imbue our models with, so that we could really drive progress in the right direction and make sure they empower as many people as possible.
All right, so I'm getting two things from what you're saying. One of them is there's a little bit of a disagreement about what the ideal long-term interlingua is between the different modalities. One of them could be language. One of them could be more of a vector space representation type thing.
Yep.
And then the challenge that you're pointing out is understanding how to apply and use these models in ways which are truly useful to people.
Mm-hmm. And not just apply and use the models we already have, but how do we inform that next wave of model capabilities, right? So there's we'll train model on whatever data we have, but then there's also the more maybe demand-driven side of, in order to unlock this next generation of applications, what do we need and how do we systematically go about then putting the right pieces together, for example, collecting the data that is needed to drive that kind of innovation.
Okay. Jianwei, your turn. What is the primary challenge you see with multimodal models?
Yeah, I think I think there are some great kind of debates in the whole domain regarding the vision, whether we should take vision as a core or take language as a core. I want to share 2 cents about the discussion Katja and Hoifung just made, right? So I still remember at the very beginning of the deep learning era, actually, when people talking about deep learning, right? Usually they mentioned probably ResNet or AlexNet or ImageNet, this kind of vision-centric kind of benchmark or model, right? But later on, actually, right now, actually, when people talk about deep learning, talk about the AI, usually we mention, the large language model, etc. Right? You can see, there's some kind of transition from vision to language. I think this also implies some kind of challenges or some kind of methodology transition. So at the very beginning, actually, all of these different modality, the researchers are trying to collect some laboratory data and train some supervised model to classify the image, classify the text, or etc. But later on, actually, people, especially in the language domain, actually come up with some new idea of supervised learning, right? So that the model can really learn from a huge amount of unlabeled data. And this huge amount of lab data actually are existing already there from the internet, and the people can create a lot of text data. And by natural, another benefit of this language data is that it can be naturally or natively tokenized. It's not like the image or speech, actually we cannot handle the hundreds of millions of pixels in a single image or in a single video. But for language, actually, it's pretty compact, as Katja just mentioned. It's pretty compact and also representative, so that people can easily tokenize them, convert the language into some kind of discrete IDs, right? And then encode these discrete labels, discrete IDs in the feature space. So I can feel that, so now, the vision is lagging behind the language in general. Even though I'm from vision side, actually, I can see, a gap is there in terms of how we can really build a supervised learning system to learn the visual representation, which can match the power of the language representations, so that we can really we can really merge or bridge the gap, as John, you just mentioned, right? So different modality definitely have the gap, but the vision side actually are not lag behind, and we need to handle that. And talking about this, I think one of the big challenge to build a very capable multimodal model is that how we can bridge the gap by, bringing the vision representation, bringing the vision tokenizer up to the similar level of the language representation and the language tokenizer, so that we can really have a very good kind of intimate interaction across two different modality. And the one last point I want to comment is that, so whether the whole system should be language native or the vision native or any other modality native, I think this also depends on what kind of applications. For some of the applications, actually, for example, in Hoifung's domain, his future, actually, people needed to handle a lot of document. But on the other hand, actually, in Katja, your gaming domain, actually, the model needed to handle a lot of pixels and handle a lot of kind of reasoning or temporal kind of planning, etc. So in my opinion, I think this really depends on what kind of scenario we are really handling. Some of the tasks actually need a lot of kind of good representation of the language because it's language heavy. But for some other tasks like autonomous driving or robotics or planning or visual planning, etc., actually it's more rely on whether the model really understands the visual signals from pixel to the middle level kind of segment region and to the high level kind of interaction across different objects in the environment or in the physical world. So I can feel there are still some kind of difference and it's still not merged. And this is, I think, why I feel it's very exciting to further push forward this domain. Yeah.
Right. So I think what I'm getting from you is the capability gap is kind of a key concern as well. Is that right?
Yep. Yep.
Yeah. Okay. So capability gap, and understanding how to really use these models in ways which are truly beneficial to people. All right. So maybe given this and given the other discussions, what are your predictions for closing these gaps and figuring out how to truly use these models in effective ways? Do you have thoughts for where we're going to be a year from now, 3 years, even 3 years is kind of far at this point. 5 years. I think that trying to predict the future is one of these things where you always feel a little squirmy because it's hard. But at the same time, I think it could be really valuable to get your sense of where things are going to go and how fast. Hoifung?
Yeah. So first, I want to sort of like kind of echo what Katja and Jianwei point out, right? So and I also want to I actually don't see it as a disagreement because I think actually all of us are talking about the same thing, which is that all those modality we want to embed them into a common semantic space, right? So that's all of them are vector representation, right? And for example, even when I am mentioning about this text as interlingual, it doesn't mean that we are actually trying to map those images and put in sequences literally to text tokens, right? So that could be one way you can do it, but actually the much more general way is to using the text signals, right? And in fact, the text actually are also mapped to the embedding space before all this kind of modeling happened, like for example in LlamaMap, right? So the goal, I would say the end goal is the same. The challenge for sort of like just looking at two, like for example, a very common paradigm is contrasted learning, and a great example is Click, right? So and that handle two modality by saying let's push those two modality into a common semantic space. So that works fine when you just have two modality, right? Once you have three, you start to get a three-body problem, right? And once you have 4 and 5 and 6, and that's where actually the combinatorial explosion happen. And that's actually why we sort of like kind of like have motivate us to say, hey, can we sort of like reduce the combinatorial explosion to maybe a linear, right? Like alignment to some potentially sort of like pretty well developed kind of semantic space, right? And text, I think for one aspect, as Jianwei alluded to, has some advantage in the sense that if you look at the public web, right, so texts are not just a bunch of words, but they actually capture a lot of human knowledge inside them, right? So for example, if we can sort of like have a gene like EGFR, it may not mean anything, right? To folks who don't study genomic, but for folks who study genomic, then EGFR actually is a very important gene, and everybody immediately can draw out, oh, this is connected to lung cancer, because a lot of lung cancer are caused by mutation in the EGFR gene, right? You also can figure out, can easily conjure up the sequence for the EGFR. You can conjure up knowledge about how the protein encoded by the EGFR actually bind to other kind of protein, and what kind of pathway or function do they control. So all this kind of knowledge are actually captured not just by this single modality of the sequence or anything, but actually by mapping to the text semantic space, there's one-to-one, you can immediately have access to all those kind of vast amount of knowledge, right? So and also I want to quickly sort of acknowledge what Jianwei you mentioned about. It's fascinating, like to think about the self-supervision landscape in computer vision versus NLP, right? So early days, as an NLP person, I'm very jealous about vision, because you have so many like translation invariants, right, rotation invariants, so you can using all those kind of things to create synthetic training data. And so until the day when in NLP, when people figure out like master language model, right, when you start to play hide and seek with the words, then that become also a very powerful self-supervision. If we directly apply that heuristic to computer vision to try to mask a patch or pixel, that's not as effective, right, at language so far, right? So exactly to echo your point, it's fascinating to think about different kind of modality, different kind of inductive biases, but I would say fundamentally they all boil down to, I mean, John, you know this all too well, right? It's like what kind of sort of like training data, sort of like general sense, right, available, right? So like the single modality data, unannotated images and so forth, they are most abundant, right? So then there are all this kind of exciting work to how to harness them. I would also argue that the text is not a perfect interlingual, but you can think about them as a second sort of source of free lunch, because all this modality often they have some accompanying text associated with them. But I would be the first to point out that that's far from being complete, right? For example, think about like 5 years ago, we don't have the vocabulary called COVID, right? Even though that kind of virus molecule could exist in some imaginary space already, right? So, and even today, right, like as Katja, you alluded to, and like if you look at, for example, a radiology report, it doesn't capture every single thing that captured in the images, right? In fact, even the best radiology may not even agree with themselves, written 6 months ago about the same interpretation of the same report, right? So I think some of the fascinating potential would be, can we actually also ground it with obviously the long-term outcome, right? For example, the patient 6 months later, did the cancer recur or not? That's much less ambiguous compared to the signal that immediately available for that modality. So that's kind of like sort of like some of my thoughts. But to directly answer your question, John, I think I roughly think about sort of like a lot of the like both Katja and Jianwei mentioned about sort of the really exciting prospect is that ultimately this is not even just an intellectual exercise. It can actually really bring huge benefit, right, potentially to real world impact, right? So, and when I think about what kind of real world impact, I can see a continuum between what I will loosely call sort of productivity gain to creativity gain, right? So, and John, to answer your question, right? So I see already a lot of kind of like high value, low risk opportunity where those are the places where typically it's like human expert can perfectly do the task. They are just could be very repetitive, could be very boring, right? But in this case, like I think a lot of the Gen AI, multimodal Gen AI already get to a point where they can already assist the human to actually do some of those tasks at scale, right? So, and then also the beauty of that is that exactly because human expert can perfectly do the task, so this is a very natural, you can do a human in the loop, right, setting. So then you can ensure accuracy, ensure that actually the AI the error can be easily corrected, and then the error can feedback to improve the AI system, right? So some of the example, for example, is like, think about again, go back to a cancer patient, right? Unfortunately, oftentimes for late stage cancer patient, at least, majority of the standard of care doesn't work, right? So that leaves, like, for example, clinical trial to be the last hope. But every year, for example, US alone, 2 million new cancer patients, right? And then every single time there are thousands of trial, right? If you go to ct.gov, 500,000 trial, right? And so how do we actually match a trial to a patient? That's today they are basically hiring this so-called trial coordinators, right? Basically manually try to look at the patient record, look at the trial, and that's completely not scalable, right? But you can imagine basically like we can learn this patient embedding that capture all the important information about the patient. And you can also embed the trial, right? Because trial actually are specified by this eligibility criteria, like what kind of property I want to see in the patient so that I will include in the trial. So then once you actually got in the embedding space, then matching you can do it 24/7, right? And you can do what people call just-in-time clinical trial matching. And actually, a few years ago, this is still a novel concept. Nowadays, actually, this have already been, applicable to many places. I just want to highlight one example. For example, we are very fortunate to collaborate with Providence, which is the third largest health system in the U.S. They started using our kind of like AI research system to actually daily now to help their tumor board to actually do this trial at scale. So example like that actually become more and more available, right? Like, for example, the digital pathology, you can actually using generative AI to learn very good model to say classify the subtypes of cancer and so forth, and then have human expert to do sanity checks and so forth. And so that's already happening, right? So and that's actually even now, right? That lots of this are already happening. But looking forward, I think the most exciting prospect is sort of loosely I would call creativity gain. That's actually in the regime where even the best human expert have no idea how to do it, right? So, for example, like digital pathology slide, you look at it, you can discern here's a tumor cell, right? Here's the lymphocyte or the immune cell. Here are the normal cell, and looking at the configuration, right? It actually gives you lots of clue about whether the immune system already are alerted by the cancer, and thereby it can determine to a larger degree whether the immunotherapy can work, right? But right now, pathology, even the best pathology, they only have a very weak heuristic about, okay, let me count how many lymphocytes within the tumor region, right? So using that as a very rough proxy, it can do, somewhat better than, right now, like if you don't look at it at all, right? But arguably, there could be tons of subtle patterns that actually even the best human expert have no idea about today, but we could potentially having generative AI to potentially unlock. So I think that would be the most kind of exciting process.
Okay, so human in the loop, generative AI, visual pathology for cancers and immunotherapy. How long is that? 1, 3, 5 years?
So I would say there are some immediate application, let's say, to pick out, like, classify one of the subtype of the cancer. Right now, like the best generative AI model are already doing very well, right? So, for example, in we recently have a Nature paper.
But how long until it's deployed?
So right now, for example, at Providence, they are already looking into actually using that as part of the workflow to say, hey, can we using that to help the subtype?
So within a year.
But yeah, and also there are some additional application, for example, like predicting mutation, right? So and then that could be sort of like uncovering some of the underlying kind of genetic activities and so forth. But I would say the holy grail here would be to actually go from that 30% response rate for immunotherapy, right, to much higher, right? So that one, I think there has already been some study, but usually on a smaller scale, right, of patient, and also hasn't actually really incorporated a lot of the really state-of-the-art kind of generative AI technique, right? So right now, I think the really exciting prospect is, like, for example, one science paper 2 years ago, right, have actually 200 patients, right? So, and if you don't have a very good representation of the digital pathology slide or including the general patient embedding, then 200 data point doesn't give you that much signal, right? But on the other hand, if you can learn from billions and billions of kind of images, pathology images from millions of slides, right? Then you can learn a very good representation. And then building on top of that kind of representation, right? You could actually start to learn much more efficiently from the long-term outcome, right? And I would say the first stage, like the productivity gain, like I also want to highlight, for example, there are exciting partnership like some of our sibling team with like Page AI, right? So they have actually also demonstrate, like for example, some of the you can do clinical grade, right? It's kind of like classification for certain tasks today, right? So, but the holy grail would be to go to this kind of like modeling tumor microenvironments and actually predicting immunotherapy outcome. I can't really predict when will we get to that, close to above 90% of the response rate prediction, but I think there is a huge growth area. And there is conceptually, we already see some tiny bit of promising result, even by using very sort of low dimension features, all right, and smaller number of data point. So I'm pretty optimistic about that if we can scale the data, but also crucially scale the and improve the representation learning, then we can get much better results.
Mm-hmm. That's great. Katja, your predictions for the future?
Let's see, 1, 3, 5 years. I'm very optimistic that in the shorter term, maybe I have a biased view, data from games can be very influential in helping us answer some of those fundamental questions on how to train and use multimodal models. The kind of degree to which we can collect rich data, multimodal data, in a reasonably controllable way at reasonable scale, is just makes these kinds of environments a prime candidate for driving insights that now in this new rules are much more generally applicable than they might have been in the past. So I would say we'll definitely see the benefits of that in the coming year. Within the 3-year horizon, one thing that's really interesting and also kind of connects to my journey as a researcher is that over the past 10 or so years, I've invested a lot of my effort, and my team has invested a lot in things like reinforcement learning and decision making. And so now with generative models, we've primarily seen the power of predictive model trained at massive scale. And yes, there is some RLHF around the edges, but I think we will see a return to some of those fundamental questions around reinforcement and decision-making settings, but building on top of the insights that we've gained from training these large-scale multimodal generative models. And I would say that in around 3 years, that'll be back in full force, and we'll have a lot of fun benefiting from maybe some of those kind of further back insights that maybe John, you and our teams have developed over time. So I'm very much looking forward to that. 5-year horizon, you're right, it's hard to predict that, especially as things seem to be moving so quickly. But one thing that I would expect in that time frame is that some of the innovations that we are working on today will make their way into the hands of actual end users. And so I believe that starting to understand what that new human AI collaboration paradigm could look like, that is something that everyone with computer access would be able to experience within the next 5 years.
Okay, excellent. Jianwei?
Yeah, I honestly, I was thinking it's very hard to predict the future in such a 5-year horizon. But so I want to share a old Chinese saying. So it says, okay, so read 10,000 book and walk 10,000 miles. So I say in the past maybe five years since GPT or since the transformer era coming. So basically, okay, we have been striving for making the model to read thousands books or hundreds of thousands books, right? So from the internet, from the Wikipedia, etc. So the model itself right now, like GPT-4 or many other kind of open source model, actually already get a lot of knowledge from the books, from the textbooks, and they have a very good understanding about how the world actually is operating, right? So, but the problem is that, okay, this knowledge are not grounded at all. So this knowledge is great, but this knowledge actually are not grounded on any kind of observation, any kind of digital world or physical world. In my opinion, I think in the next few years, even actually it's already happening now. So people are trying to ground this kind of big brain learned by looking at reading a lot of books, right? So to really, okay, until this kind of digital world or physical world, like in the represented by, okay, image, by video, or by many other modality as Haifeng just mentioned. So I can imagine, okay, in the next 1 or 2 years, actually people are really trying to squeeze the knowledge out from the big giant large language model to really, okay, build the connection between this kind of heavy and rich knowledge and the visual observations or other type of observations. So this is one thing I can imagine, which would be very likely happening very soon. So people are trying to build the connection, and the people are trying to really, okay, make the other part of the model stronger and have some kind of connector in between. And the next after that, I can imagine that, okay, so this kind of progress will probably start happening in the digital world, because, okay, as we just mentioned, so in the digital world, actually people can obtain the data very quickly. People can create a lot of data from the internet. And gradually, actually, if we used up all of the data from the internet, actually, we really need to, okay, put this system into the physical world, into the environment that we are living, right? So we really want put this model out, put this system out, and let themselves actually explore in the physical world to interact with the environment and to learn some more knowledges. And I want to echo Katja, what you just said. Actually, the gaming environment, I would say, is really great kind of simulator or emulator to the real environment that, okay, have a lot of kind of there are a lot of interactions between the agent and the environment, right? So I think this kind of information can really be beneficial to make the model to learn more grounded knowledge about the world. And later on, actually, we can probably really deliver this model, this system to the real kind of world, like what we are recently, our team actually, we are doing some kind of research, like, okay, how we can convert the multimodal language model like Lava or 5.3V to a vision language action model, right? So it already learn a good knowledge about the vision and language domain, but how we can make it more capable of make a decision, make the planning to accomplish some daily task, like what we are doing in our daily life. So this is kind of thing, actually, I can imagine it could happen very soon in maybe a few years. And yeah, overall, I feel it's very exciting area for us to really push forward this direction. And also, I'm very kind of optimistic that, okay, so we are seeing very great things in the next few years.
So, do you have timelines for these? Like, what's your expectation for how long it'll take?
Yeah, so I think talking about the ultimate goal in my mind, like I just mentioned, so how we can build a real AI agent that can traverse in the digital world and also traverse in the physical world. And we already see a lot of work in the digital world, like the system we have built. And on the other hand, actually in the physical world, actually we are yet to see a real kind of robot that can undertake a daily task like ourselves. And I can imagine this will require a lot of effort from different aspects. But I'm a little bit probably more optimistic that, okay, it could happen in maybe 5 years to 10 years. That, okay, we really can buy some kind of real robot, right? So and put it in our home and help us to do some household tasks, something like that. Yeah, I'm probably, yeah, a little bit optimistic. Yeah.
So 5 to 10 years until you have a generative AI robot that can do useful things
Yeah. Yeah.
in your home.
Yeah.
Excellent. All right. I think we've probably gone longer than they wanted us to. Thank you, everyone. It's great to hear from you. I've actually learned quite a bit during this discussion.
Thanks so much.
Talk to you later.
Really enjoyed
Yeah.
the discussion.
Thank
Thanks
you.
so much,
Super
everyone.
fun. Yeah, thank you for the invitation.